Hi there, in this video we're going to cover section 5.1, the introduction to probability distributions, and also introduction to significance. How strong is the evidence of something, of our data? So for this example, I have the friend or foe example here, and one of the things that is posted in Canvas is this link to the YouTube video. So please watch the YouTube video first, and then you can come back and continue this video. So if you haven't watched it already, then pause or end this video, go back and watch the YouTube video that is linked to the Google Notes in this handout that is shared with you in Canvas. Watch that video and then come back to this video. So the example, the study is, do children less than a year old recognize the difference between nice, friendly behavior as opposed to mean, unhelpful behavior? Do babies make choices based on such behavior? And so there was a group of researchers, and they published a study in November of 2007, where they investigated whether infants take into account an individual's actions towards others in evaluating that individual as appealing or aversive. In one component of the study, the children, 10-month-old infants, were shown a climber character, and this is what you have seen in the video. A piece of wood with googly eyes glued onto it that could not make it up a hill in 2 tries. And then they alternately shown 2 scenarios for the climber's next try. One where the climber was pushed to the top of the hill by another character, the friend, and another scenario where the climber was pushed back down the hill by another character, the foe, right? So the infant was alternately shown these 2 scenarios several times, then the child was presented with both pieces of wood, representing the friend and the foe, and asked to pick one to play with. So in the video, you kind of see what happened and the results. So the question then is, right, what is the research question? So as we get into our semester projects, and you're going to be working with, you can work with people in the class, or you can work alone. Preferably, I would like you to work with one other person. You can also make groups of 3 or 4, and I will send a survey asking you what you prefer, and then I can put you in groups. So, but we're going to go through the 6 steps of a research study. So step 1, so there are 6, right? Step 1, ask a research question. Step 2, design a study and collect data. I'm going to go through them really fast right now, but then we'll come back and work through for this particular study. So again, step 1, ask a research question. Step 2, design a study and collect the data. Then step 3, explore the data. Draw inferences from your data. And then where is step 5? This is step 4. I guess it's kind of long. So step 5, formulate conclusions. Once you've done all your statistical analysis, what are your conclusions? And this is where you're going to get to state your evidence or your significance, and then look back and ahead. What was missing, or what other questions were generated from the data that you gathered. All right, so let's go back to the top and start with step 1. So ask a research question. What is the research question that this study is trying to answer? And oftentimes when you read a study, you'll be able to tell from the writing of it where it is. So notice that here it says, do children less than a year old recognize the difference between nice, friendly behavior as opposed to mean, unhelpful behavior? So that is what the researchers are trying to answer. So we're going to say that is the research question. Right? Do children less than a year old recognize the difference between friendly versus unfriendly behavior? And then we're going to try to gather data. So design a study and collect data. So identify the observational units and variable in this study. Then is the variable categorical or quantitative? So now in this section, we kind of start pulling everything together. Things that we did in chapter 1 and chapter 2, and then things that we did in chapter 4 with probability. So what are the observational units here? Things or people being studied. And what's being studied is the babies. So we can say 10-month-old infants. What is the variable being measured? The variable being measured is which toy the baby selected, right? Did they choose the friendly toy or the one that was displayed as unhelpful. So which toy or character was selected? And what type of variable is this? Categorical or quantitative? So categorical, right, you have choices, you have categories. In quantitative, you have a number. So in this case, which toy or character? Well, what are the options? They have is the friendly or unfriendly. So we would say that it is categorical. Let me highlight that. And if it's categorical, then we have to answer, is it binary or not? And yes, it is binary because you have two options, right? The friendly or unfriendly toy. So there are only two categories. So we say is categorical, binary. Now in the study, researchers found that 14 of the 16 infants in the study selected the nice toy. When you watch the video, you probably heard one of the researchers say that almost 100% of the babies selected the friendly toy. And so here I've condensed the data just so that it's something that we can work with for our note, but the original study had a lot more than 16 infants. I just tried to pick numbers that were similar to the percentage that they had. So 14 out of 16 is about 85%, which is very high, right? So I just kind of chose a small number so that we can work with it and so that we can do our simulation. Step 3, explore the data. So determine the proportion of infants who selected the nice toy. So the proportion of infants who selected the nice toy. Is this a statistic or a parameter? So write your answer using the appropriate symbol. And in chapter 3, we went over the different symbols when you have a sample versus when you have a population. So here, determine the proportion. The proportion will be 14 out of 16, right? And so what is our notation? We're going to call it P. So P equals 14 out of 16, and you can convert that to a decimal, which I had said was 0.875, 87.5%. So that is our proportion. That's the proportion of babies that chose the friendly toy. Now, the methodology section also states that for the 10-month-old, the climber was a yellow triangle, helper and hinderer were a red square, and a blue circle, counterbalance. Also counterbalance were which event, helping or hindering, they observed first, and the positions of helper and hinderer were presented to the infants on left or right. Why are these important considerations? So why does it matter to change the color and change the shape of the different characters? So alternating the shapes and colors could be helpful to eliminate any potential bias, right? Like if the babies have a favorite color or a favorite shape, a shape that they work with at home and it's easy for them, or things around the room, right? If they have a particular color of the room that makes them feel comfortable. So if their room is yellow or green, they might be drawn to that color. So alternating the colors kind of removes any of that potential bias. So let me put that in there. So to eliminate any potential bias, favorite color, shape. And so now we move on to step 4. Suggest 2 possible explanations for this result that the researchers observed, meaning the 14 out of 16 babies chose the friendly toy. When I say this result is that 14 out of 16 babies chose the friendly toy. So what are 2 possible explanations for that? So think about that. Pause the video if you need to think a little more, and then we'll go over the 2 possible explanations. So one reason could be the researchers are correct and the babies can tell the difference between friendly and unfriendly behavior. And so they choose the friendly toy because they perceive it as being friendly, so they can recognize the friendly versus unfriendly behavior. So we're going to state that as reason 1. And then what about another reason? What could be another reason that they are choosing the friendly toy? And one of the things that could be happening is they're just guessing. So reason two, they happen to choose the friendly toy at random. They're just guessing. They just pick a shape, not really based on whether it was friendly or not. So they're just guessing. So those could be the two reasons. So suppose for a moment that the researcher's conjecture is wrong and infants actually have no preference. So that would be reason two, right? They have no preference. They're just choosing the friendly toy at random. Will it be possible to have obtained a result as extreme as what the researchers found, meaning the 14 babies out of 16 chose the friendly toy? Could that have happened if they were just guessing? And the answer is yes, right? It could happen, but it's not very likely. So we say it could happen, but it is very unlikely. So when we talk about unlikely to happen or likely to happen, now we're bringing in probability. So for part G, again, suppose that infants have no preference, meaning they're just guessing. How many of the 16 babies would you expect to select the nice toy? So think about that. If they're just guessing, how many do you expect will select the nice toy? So I would say that if the babies are guessing, then maybe around 8 babies would select the friendly toy. Because if they're just guessing, why do I think that just 8? Well, there are two choices. Do you even have the friendly or the unfriendly toy? So 2 to choose from, so 50%. And 50% of 16 is 8. So if they're guessing, think of a coin toss, right? Like a coin has heads or tails. So when you flip a coin, you have the chance of getting tails is 50-50, 1 out of 2. So that's the same thing here. You're choosing friendly versus unfriendly. So 1 out of 2, so 50%. When you have 16 babies, we expect about 8 of them would choose the friendly toy. So the key question here is to determine what results will occur in the long run. So under the assumption that infants actually have no preference, and we're going to call this the null model, the null hypothesis. So this is the model with no preference. And we will answer this question by simulating, artificially recreating the selection process of 16 infants over and over. And the big thing here is that assuming that infants actually have no genuine preference. So that's our null hypothesis. And this process of, in the long run, this simulating, artificially recreating our results, the 14 out of 16, this process will generate what we call a probability distribution. So let's rewrite our two possible explanations from question E as hypotheses to be tested, and I'll help you with this. So question E is right here. It was the possible explanations of why we got 14 out of 16 babies choosing the friendly toy. Reason 1 was babies can tell the difference between friendly and unfriendly behavior. And reason 2 was they happen to choose the friendly toy just at random, by guessing, right? They can't tell the difference between friendly and unfriendly behavior. They're just guessing. So let's rewrite our reasons here. And because we want to create a null hypothesis, this is the one that no preference. As we want to assume, so we want to artificially recreate this result, assuming that infants have no genuine preference. And so that's what we're going to call the null hypothesis. So for the hypothesis testing setup is as follows. You have your null, which denoted H in the subscript 0, and it's called H null, like NULL here, so H null, the null hypothesis. And this is the selection is happening by chance. So they're just guessing. That's the no preference model. The alternative, so that's called the alternative hypothesis. Usually that's the research question. So in this case, the null hypothesis will be the babies are choosing the friendly toy at random. They're just guessing. And the alternative hypothesis is going to be the researcher's question, that babies can tell the difference between friendly and unfriendly behavior, and thus they're choosing the friendly toy because they perceive it as friendly. So those become our hypotheses. babies select a friendly toy at random, simply guessing, that's the null hypothesis, that's the by chance model. And the alternative hypothesis is babies recognize friendly and unfriendly behavior and choose the friendly toy. Now, a probability distribution is a description that gives the probability for each value of the random variable. It is often expressed in the format of a table, formula, or graph. In this example, for this study, we're going to choose the graph format to display our probability distribution. So now let's go to the simulation. Describe how we could use a common device like a coin flip to simulate the infant selection process. Which hypothesis does this replicate? So let's answer the hypothesis part. Which hypothesis does this replicate? If you're just flipping a coin and noting where it lands, that's at random, right? So this is simulating the null hypothesis. So our simulation. Coin flip, what does the coin flip represent? The coin flip will represent the baby's toy selection. Right, as you flip the coin, it's as if the researchers are presenting the babies with the two toys. And then heads, let's let heads be the friendly toy. And then tails will be the unfriendly toy. So what is the probability of heads? In a coin flip, this is going to be 1 out of 2, so 50%. What is one repetition? One repetition will be 16 coin flips, representing the selection of 16 babies. All right, so go ahead and grab a coin, pause the video, and flip a coin 16 times. Record the number of heads that you obtain, which represent the number of your 16 hypothetical infants who choose the nice toy, right, the friend toy, or the mean toy. And then write out what your results are. So how many times did you get? We're keeping track of heads, the number of times that you get the friendly toy. Well, we're keeping track of both. But then fill in this chart. How many times did you get heads? How many times did you get tails? What's the total? Find the proportion, which is really also kind of like your relative frequency. And then what is the probability as a decimal? And so we're going to combine your simulation results with your classmates. And so what I've done is I'm just going to post the one that I did for my in-person statistics class. I'll post that one here, and then we can see how it looks. So go ahead, pause the video, and do your coin flip. Flip it 16 times and record your results in this table. So I will put my results here just to show you what it will look like. So I got 5 heads, 11 tails for a total of 16 coin flips. The proportion then will be 5 out of 16, right? Is the number of heads divided by the total. And then the tails will be 11 out of 16. So notice that when I add them, so my total will be 5 plus 11, so I get 16 out of 16, which will be equal to 1. So this is kind of like a probability. The proportion, the probability of getting heads in this particular instance will be 5 out of 16. So it is less than 1. Remember, probability should always be between 0 and 1. So probability as a decimal, when you do 5 divided by 16, so this will be 0.3125. And you put in your calculator, 11 out of 16 will be 0.6875. And then the total, so when you add these up, you will get 1 still. Now combining the simulation results with our classmates, so I'll share the one that was done in my in-person class. So here it is, I took a picture of the board. And so we have, this is the simulation for everybody that did it. And so create a dot plot, so that's what we did. Copy the distribution below. So hopefully you will have this, and I'll post the filled up notes so that you have these as well. And so every probability distribution must satisfy each of the following three requirements. There's a numerical, not a categorical random variable x, and its number values are associated with corresponding probabilities. So here, right, we're keeping track of the number of heads. So this is not categorical. So even though the original study, the babies are choosing friendly versus unfriendly toys, that is categorical. But once we're doing our simulation, we're keeping track of the number of heads that we get, right? We said heads is the friendly toy. So we're keeping track of how many times the friendly toy is chosen. And so that is a numerical value. And then the sum of the probabilities is 1, where x assume all possible values. So there is our probabilities. They add up to 1. And the individual probabilities should be always between 0 and 1. Now, looking back at the distribution, where is the distribution of number of heads in 16 tosses center? And so notice that we're looking at the number of heads again. And so going back to the graph, notice that I labeled the graph number of heads. So where is it centered? It appears to be right around 8, which is what we had expected, right? When we said if the babies, where did we say that? If the babies were guessing, we would expect that around 8 babies will select the friendly toy if they're just guessing. And now looking at our probability distribution, we see that it is right around 8. And well, in this case, it's more than like 7, but if we average it out, right, if we find the mean, we'll see that it is right around 8. And so let's put that in here. So using the actual graph here, I put it, we're centered around 7, but that is close to 8, which is what we had expected. And which brings me to one of the parameters of a probability distribution is the mean for a probability distribution, which is also called the expected value, which is mu equals the sum of x times the probability that x occurs. So back to your individual results from part J. So the ones, where's part J? Oh, I passed them here, where you did your individual results. We want to find the expected value for the number of heads. So mu is going to be then the number of heads times the probability of heads in a coin toss, which is 50%, right? Heads or tails, plus the number of tails and the probability of tails in a coin toss, because you're either going to get heads or you're going to get tails. So let's write what this is. Now I'm going to do it for my own results. So I had 5, that is the number of heads that I got, times the probability of heads in a coin toss. The probability of heads in a coin toss is 0.5, plus then the number of tails, 11, times the probability of tails in a coin toss, which is 0.5. And so when I add these up, I'm going to get 8, which is what we had guessed or anticipated. So this is the expected value. So our 8 here is the expected value. And notice that makes sense because, not to be punny, but 8 is what we expected. So that's called the expected value. Now, how many students in this class had results as extreme or even more extreme as the results found by the researchers? So circle these dots on the dot plot. And so going back to the class results, nobody got results more than 14. Now you at home, if you got something like 13, 14, or 15 number of heads, let me know. Please email me and then I'll add them to future data because we'll revisit this example later. And so in our case, the dot plot that I've shared, nobody got more than 14. I should say 14 or more. So since no one got 14 or more, then the next question kind of makes more sense. Looking at the dot plot, does it seem that the result obtained by the researchers would have been surprising if in fact the infants had no preference? So meaning if the babies were just guessing, would it be surprising to get a result of 14 babies choosing the friendly toy? Yes, right, it would be very surprising because we expect it to be around half, around 8. So what does this suggest about whether the researchers' results provide much evidence that the infants do generally prefer the nice toy? And explain. My hint is to look at the proportion of the class that got 14 or more heads. We said nobody got 14 or more, so the proportion of those that got greater than 14 will be 0, right? So that means that, would it be surprising? Yes, it will be very surprising to get a result of 14 if babies are just guessing. So this kind of leads us to believe that maybe the researchers are correct, but just this simulation doesn't prove it all. So we're going to have to do a computer simulation. Ideally, and this is kind of the behind the scenes of studies, when you do a simulation, you want to try to replicate those results a number of times, a large number of times, so that then you can make statistical analysis with it. So what we're going to do is we're going to try to run 1,000 samples total, but we're not going to do it by hand, right? So like back in the dot plot that I shared, and I hope I'm not giving you a headache by scrolling. In this dot plot, notice that I had very few students who did it, and well, in class. And so there's not that many repetitions, right? Definitely not 1,000. So if I had 1,000 students, this will look a lot fuller. And so that's what we're going to do. We want to replicate this result a large number of times and see how likely is it that we're going to get 14 if I replicate this 1,000 times. So what we're going to do is we're going to use the one proportion applet. So go ahead and click on this and you can open it. And it's going to take us to the one proportion applet. And going back to the handout, let's make sure we want to make it look like this. And we're going to start off by just doing one. So over here, start with one repetition just to get a hang of how the applet works. And then we're going to repeat this 5 times just to try to get used to what it looks like. Then we're going to do 50 repetitions until we have a total of 1,000. So you want to make it look like this. So on your one proportion applet, go ahead and make sure that you have the probability of heads is 0.5, right? 1 out of 2, if you had heads or tails. The probability of heads is 1 out of 2, 0.5. Number of tosses is 16 because we're simulating our sample size. We have 16 babies. The number of repetitions right now will just be 1. So this is going to simulate what you did in your individual coin toss. And then we're going to click on draw samples. Also make sure that the radio button for number of heads is selected instead of proportion of heads. And so let's go to the one proportion applet and make it look like that. So probability of heads 0.5, number of tosses 16. We're going to do 1 repetition. Number of heads is selected and click on draw samples. And notice that it's showing us the coin flips. So this is essentially what you did in doing your own coin flip. And so for this particular coin flip, the number of heads was 3 and the number of tails was 13. And notice that it gave me a dot for the number of heads. It's only keeping track of the number of heads. So 3. And now we're going to do, I want to get 5 total. So I already have 1. So let's put 4 in here for the number of repetitions. And now what I'm going to do is go ahead and unclick show animation, because then it's not going to be flipping the coin every time. That takes a while. So unclick show animation, draw samples, and it just does it much faster. And so now we have this. So for 5, that was our original one. Some other repetition had it at, that looks like 7, then 2 at 8, and 1 at 9. And so on. So now I want it to be a total of 50. So notice here, the total repetitions that I have so far is 5. So how do I make it 50? Change that to 45. So 45 plus 5 will be 50. Draw samples and notice that now I have 50 total repetitions. And so over here, I should have 50 dots. And notice that it's still pretty centered at 8. There's a lot of eights there. Now let's go to, we want a total of 1,000. So what number should I put in here so that I get a total of 1,000? Let's do 950. And make sure that your show animation is unclicked. Otherwise, this is going to take forever because it's going to be doing 16 coin flips 950 times. So you don't want to do that. So make sure that your show animation is unclicked and then hit draw samples. And here they are. So now this is 1,000 flip, 1,000 repetitions of the 16 coins being flipped. And now notice that this is really nice and bell-shaped, centered at 8, and so this is our probability distribution. So going back to the notes, describe the shape of the resulting dot plot, which is our probability distribution, and comment on whether it's centered where you expected. The shape, we can say that it is pretty bell-shaped. The center, it is centered around 8. That's what we expected. So yes, it is what we expected. And what about the variability? Variability refers to the standard deviation. And so what is the standard deviation? Let's go back to the applet. So here is our dot plot, and it appears to be centered at 8, but how do I make sure? Notice this box right above the dot plot that says summary statistics. Go ahead and click on that. It says summary statistics. And notice that the mean is 8.088. So that is very close to 8, where we assumed it was going to be. And SD is the standard deviation. So 2.033. So that is our standard deviation. So we can go back to our notes and put that in here, 2.033. Yours may look different, right? Because as we each simulate this for 1,000 times, we're going to have different flips of the coin. It will be like you flipping your coin versus me flipping my coin, right? My results were 5 heads and 11 tails. And yours could have been different, 7 heads or 3 heads or 4 heads. So that is going to be the same for our simulation. So when I do my 1,000 simulations on the applet, is the coin flips, the 1,000 times that we're flipping the 16 coins, is different. Is me doing it versus you doing it. We're going to get different results. So when you look at the mean here and you're like, well, how do you get 8.088? Mine is different. That's okay. It should be really close to 8 though. You should have either like 7.998 or 8.003. Should be really close to 8. Same with your standard deviation, right? It should be 1.98, 1.97, or 2.011. With whatever it is, it will be very close to 2. And again, I would just want to explain the difference, right? It's you flipping 16 coins versus me flipping 16 coins. Our results are going to differ slightly, but in the long run, we're going to be close to the same parameters. So now based on our results, would you say that it will be very surprising if infants actually have no preference? That 14 out of 16 infants in the study will have chosen the nice toy just by chance? No, right? Look at our 1,000 repetitions here. There wasn't even anything after that's probably 13. So you may have had something over here. So pay attention to that. So let me copy this and bring it over to our notes. maybe, if it lets me copy it. Oh, here we go. If I right click and then go to copy image, then I can go into here and then I think I can paste it. Yep, cool. And so based on my results, it will be very surprising, right? There's no, notice over here, there's nothing above 14. So I would say based on my results, it will be very surprising if babies are choosing by chance. So based on, and I should really say our results, it will be very surprising if 14 out of 16 babies chose the friendly toy by chance. If they're just guessing, there's just no way that we're going to get that extreme of a value when everything is centered at 8. Now on the last part here, in the as extreme as box, write 14 and click count. And what this is going to do on our applet is essentially going to count the number of results that were as extreme as the ones that our researchers found. So going back to the applet, count samples as extreme as, so greater than 14. So we want to see how many results were like what the researchers got or more. That's what the greater than does. So count, and I got 0. And if you're doing it at home, you may get some numbers there, like 2, 3, maybe 5, but it should be very, very small. And notice, for example, if I even do change it to as extreme as 8. Now notice this, there are 622 values that are 8 or more. So that is pretty expected, right? We think it's centered at 8. So if I go back to 14 and count, now notice 0. 0 out of 1,000. And so if you want to be even more sure, you can do 10,000 reps. So I already have 1,000, so do 9,000 and draw samples. And do with 10,000, notice even out of 10,000, I only got 22 results, as extreme as what our researchers got. So that means 10,000 groups of 16 babies, right? Only out of 10,000 groups of 16 babies, only 22 of those 10,000 groups had results as extreme as what our researchers got, assuming that babies are just choosing at random, that they're just guessing. And so what can we say? What is the significance of this? So the range rule of thumb for identifying significant values is that if we are more than 2 standard deviations away, then it's a significantly high value, which, going back to our dot plot here, the standard deviation is 2. So when you go from 8 or minus 8, when you go 2 from 8, that puts you at 10, and then another 2, that puts you at 12, right? So anything higher than 12 will be significantly high, so not as common as the rest of the data. So that's what our range rule of thumb means. So the values, if you're close to the mean, they're not significant, meaning they're expected to happen. And then when you're 2 standard deviations away, they are significantly high values. So it's rare that they're going to happen. If you're 2 standard deviations below the mean, those are significantly low values. So very rare, again, that they're going to happen. So if under a given assumption, the probability of a particular outcome is very small or significantly greater than what we expect, with that assumption, we conclude that the assumption is probably not correct. So our assumption here is that the babies are choosing the friendly toy by guessing. So what we just found is that assumption is probably not correct. So let me highlight. I'm trying to highlight this. So what we found is that assumption is likely not correct. So that means the babies are not choosing at random. So what does that mean? That means that the researchers are correct, right? The babies can tell the difference between friendly and unfriendly behavior, and thus they're choosing the friendly toy because they recognize that behavior. And so that's what's going to be our conclusion. Now here, the standard deviation just gave you a formula for finding the standard deviation by hand. I encourage you to try to do it for this particular problem with your results of heads and tails. Sorry, I'm hoping. So here, we found the mean also by hand, doing it this way. So take this same result, and now we're going to do the standard deviation over here by hand. And in your book, in your textbook, there should be some examples on showing you how to do this as well. And but for the sake of time, I'm going to move on to formulate our conclusions. So what can we say about the study? So in light of our previous answers, would you say that the experimental data obtained by the researchers provide strong evidence that infants in general have a genuine preference for friend over foe toy? And we can say yes, right? The value of 14 is 2 standard deviations away from the mean, making it rare or highly, what was it? Highly unlikely to happen. So, or like an outlier, essentially, it's very highly unlikely that is going to happen. So this means that the assumption is wrong, is likely incorrect. The assumption being that the babies are choosing at random. So we can say that we are pretty certain then that babies can tell the difference between friendly and unfriendly behavior. All right, and then looking back and ahead, what else could happen, right? The researchers next wanted to see whether the preference was made based on social evaluation or on a perceptual preference. So the looking back and ahead is oftentimes once you're done with the study, it may generate more questions. And so you explore those questions like what, is it just a perceptual preference? And so you may run the experiment or the study a little bit differently, change the shapes or remove the googly eyes so that they're not as cute, right? And they're not as likely to even pick a toy because they don't seem like a toy. So things like that. So with the research study, observational study or experiment, oftentimes once you're done with the analysis, you get more questions. What else can you answer from that? So that's kind of what this is. So on your own, how would the analysis and conclusion change for this study? Explain your reasoning and why your answers make intuitive sense in reading this part, and include it with your note submission at the end of the week. Email me if you have any questions, and I highly encourage you to bookmark the applet, the one proportion applet, as we'll be using it more often. And it also saves you from having to find those things by hand, the mean of the probability distribution and the standard deviation. All right, email me if you have any questions.